We are looking, no, keep them, it took staple today. Keep it, keep both pages. Today's notes, we're looking at section 1.3. It's dealing with more function properties. The first property we're looking at is continuity. The graph of a continuous function will have no breaks, holes, or gaps. You can trace the graph of a continuous function without lifting your pencil. So if we look at this graph, f of x is continuous for all x values. I could put the pencil down and trace the entire thing without ever having to lift it up. To understand what it means for a function to be continuous from an algebraic perspective, it helps to examine the graphs of discontinuous functions, or functions that are not continuous. Functions can have many different types of discontinuity. So let's look at the first graph. On this one, we see a major break in the graph. What's happening on the graph at that location? What's that called? An asymptote, okay? We have a vertical asymptote. The vertical asymptote is a major break in the graph, which means the function is not continuous at the point where that vertical asymptote occurs. Okay? In this case, we would call this a non-removable discontinuity. Bless you. We call that a non-removable discontinuity. Let's look at the middle graph. Is it continuous everywhere? No. Does it have any kind of break in the graph? Yes. Major break at this location where x equals c, some random point c. Major break in the graph. In this case, it's just a jump. It's not a vertical asymptote. Okay. If you notice the domain of this function, what is the domain of that function? The domain is negative infinity to positive infinity. It's all real numbers because even though it doesn't equal x equals c up here, it does equal it down there. So the domain's all real numbers. However, we have a point of discontinuity. It's just a jump in the graph. And so this one, we're also going to identify it as a non-removable discontinuity. Then let's look at the third graph. Could we say the third graph is continuous everywhere? Nope. What do you see? We see a hole. There's a hole in the graph right there. When there is a hole in the graph, we call that type of discontinuity removable. It is a removable discontinuity. We say it's removable because it's basically one point has been plucked out and removed from the overall graph. So it's removable. Anything else, we're going to call it non-removable. So the vertical asymptote, the major jump or break in the graph, will be non-removable. A simple point being removed to create a hole, we call that removable. Let's look at example 1. And now to continuity, we're going to add in end behavior, which should be a review from Algebra 2. Using the given graphs, state the discontinuities and the end behavior. Also, state the behavior of the function as it approaches the discontinuity. So, here's the function, f of x equals 3 divided by x plus 2, and there's the graph. Well, what do you notice on the graph? We see a what? Vertical asymptote. Where is that vertical asymptote occurring? It's occurring at -2, isn't it? So if I come in here and draw that, that's at x equals -2. Now look at the function. 3 divided by x plus 2. Vertical asymptote you just said is at x equals -2. How does that tie into the function? That's right. If we plug -2 in for x, that makes 0 in the denominator. Can you ever divide by 0? No. So, based off of the denominator, we can see x cannot be -2. In this case, that's what's creating our vertical asymptote. So, x equals -2 is a point of discontinuity. What type would it be? Removable or non-removable? Non-removable. Okay. Now we're going to take the graph and we need to describe the end behavior. The end behavior means what's happening on the far ends of the graph, way out there. So way as far back as we can go, so as way as far out we can go. What's happening out on the ends of the graph? We have to write it in limit notation. So the first one will be the limit, Lim. Underneath of it, x approaches -infinity of f of x. This is the proper notation I'll be looking for. Okay? This is the notation I'm going to be looking for when you're writing your limits. Equals. All right, so as x approaches -infinity, so we're going where all the x values are negative, way far out here. The further out we go, what y value is our graph approaching? 0. As we go further and further down, it's approaching a y value of 0. So that limit is 0. Now let's go the other direction. The limit as x approaches positive infinity of f of x. Now x is getting larger and larger and larger and larger and larger and larger way out here. What y value is it approaching on that far end of the graph? 0. That's how we use limits to describe the end behavior. Now we need to state the behavior of the function as it approaches the discontinuity. So our point of discontinuity is x equals -2. So this may be a little bit different. You may not have seen this before. We're going to find the limit as x approaches -2. But this time, as we approach -2, we have to approach it from both sides. One time, we're going to approach it coming from the left. A different time, we're going to approach it as we're coming from the right. To signify which direction we're approaching it from, we're going to use either a negative or a positive as a superscript. So just like if you have x squared, this squared is a superscript. So what's going to happen is I'm going to approach this from the left, and that's from the negative side. So I put a little negative sign up there as a superscript. That means I'm approaching -2 from the left-hand side of our function f of x. So looking at the graph, now I'm approaching that vertical asymptote. And if I'm approaching it from the left-hand side, erase all that. If I'm approaching it from the left-hand side, I'd be coming down this way. Where is that approaching? Where's it going towards? It's going to -infinity. So that's the limit. Now we need to approach -2 coming from the right. So the limit as x approaches -2 from the right-hand side, so I'm going to put a little plus sign. Now I need to approach -2 from the right-hand side, or from the positives. So now I'm coming into it this direction. And as I approach -2 from this direction, where's the function going? Positive infinity. Okay. So if we're approaching negative infinity or positive infinity, that's finding an end behavior. As we're approaching a specific number from the left and right, that's the behavior as we approach an asymptote. Okay. Questions on that? Let's try another one. On part B, the function is f of x equals -2x divided by x minus 4. And here's the graph. So based on the graph, do we have any discontinuities? Yes. What do we have? Non-removable where? Okay, so we have non-removable discontinuity at x equals 4, because what's happening at x equals 4? It's a vertical asymptote. Okay, vertical asymptote. So now we need to do the end behavior. The limit as x approaches negative infinity of f of x. So x is getting smaller and smaller. Can we see this time what the y values are approaching? That's a little hard to see that, isn't it? That one is actually -2. Actually approaching a y value of -2. Now, a little hint on where that -2 can come from. Look at your function. Do you see the x's on top and bottom?
Yeah.
The x's have the same exact power. Now look at the numbers in front of them. -2, and what number's in front of this x? A 1. If you divide out -2 divided by 1, what do you get? -2. Bingo. That's where we're getting that number from. Okay. Now let's approach positive infinity. The limit as x approaches positive infinity of f of x. So as x gets larger and larger, what y value is it going towards? -2. Now we need to do the limits as we're approaching that vertical asymptote from both sides. So the limit as x approaches 4 from the left-hand side, or from the negatives. Let me erase some of what I already have here. Clean it up a bit. Okay, so here's x equals 4. I need to approach it from the left-hand side. So if I'm going left to right, approaching it from the left, where's the function going? Positive infinity. Now we need to approach 4 from the right. And as we approach 4 from the right, where is it going? Negative infinity. Okay. Any questions on that? Any at all? Okay. Next page. Part C. G of x equals x squared plus 2x divided by x plus 2. When that is graphed, this is the graph. Does it look like that matches?
Yeah.
It does. So let's look at it. Is there something I can do with this function first?
You can
I could simplify. How can I simplify?
take
Good. In the numerator, we want to factor out the x. So if I factor out an x, what am I left with? X plus 2. So now I have x times x plus 2 divided by x plus 2. What's happening? X plus 2's cancel, and so what I have is basically y equals x. Does this look like the line y equal x? It does. Okay. Now, does the graph look like it has any points of discontinuity? No. It looks pretty continuous to me, right? But if we look at the original function, before we did any factoring, what do we know x cannot equal? X cannot equal -2. Okay? So something is happening at the graph at x equals -2. What I'm going to do is I'm going to pull up my graphing calculator. You don't have to get one right now. You can just watch on my screen. So let me pull it up. And I'm going to go and graph it. So let's see. X squared plus 2x divided by x plus 2. And we get the same exact graph that's on your notes, correct? Now watch this. If you do zoom decimal, which is number 4, now watch what happens. What do you see? Look at that. We see a hole. Where's that hole at? At -2. So when you just press graph and you're trying to look for points of discontinuity, calculator's not going to show it. If you do zoom decimal, then you will be able to see it. Because what we've done is we've expanded our x and y axes into decimals. And so by zooming into decimal, we can now see the hole is there. Okay, we can actually see it. So let's go back to the notes. Look at this. So on your paper at x equals -2, I want you to draw in a hole. We have a hole at x equals -2. And we get that hole because those factors canceled out. We had a common factor on top and bottom, and when they cancel out, that's what produces the hole in the graph. So when a common factor cancels from top and bottom, it produces a hole at that spot. Now, if it's a hole, what kind of discontinuity is that? That is a removable discontinuity at x equals -2. All right, part D, f of x equals x squared plus 5x plus 6 divided by x squared minus 4. So what should I do first with that function? Factor it. Factor the top and bottom. Go ahead and do that. What does the numerator factor down to? So the numerator is x plus 3 what? X plus 2. And what about the denominator? X squared minus 4 factors down to x plus 2, x minus 2. Is there anything that cancels? X plus 2 cancels. So because that cancels, what's that giving us? Okay, x plus 3 over x minus 2. But in terms of the graph, when the x plus 2's cancel, what is that going to be on the graph? So that means we have a hole at where? At x equals -2. What else do we have on the graph?
vertical,
A vertical asymptote at where?
two,
At x equals positive 2. So the factors canceling gave us a whole. There's still a factor left in the denominator, so the value of x that makes that denominator equal to 0, that's what's giving us the vertical asymptote. So any factor that's still in the denominator is going to give us a vertical asymptote. The factor that cancels between top and bottom gives us a whole. The whole, what kind of discontinuity is that? Removable. And the vertical asymptote at x equals 2, what kind of discontinuity is that? That one's non-removable. Okay, so now why is it that some discontinuities show up as asymptotes and others do not? Factors that cancel give a whole. Factors that are left in the denominator give a vertical asymptote. So now I want you to do the bottom section on your own. Without graphing, just looking at the equations, determine where the functions are discontinuous and state whether it's removable or non-removable. So let's go with Austin. Austin, on this first function, f of x equals x plus 2 divided by x minus 6 times x plus 2, tell me one point of discontinuity that we have. At x equals 6, non-removable. Because that's going to give us what on the graph? It's going to show up looking like what? Asymptote. Good. All right, the next one, let's go with Laura. What else do we have for this graph? At x equals negative 2, a whole, which would be what kind of discontinuity? Removable. Perfect. Do we have any other discontinuities for that graph? Excellent. So that's it. Let's look at f. f of x equals x plus 3 divided by x squared minus 9. Let me go with Dwayne. Do we have one? At x equals negative 3, we have a removable discontinuity because it's a whole. Correct. Good job. And let me go with Lily. Excellent. At x equals 3, non-removable discontinuity because that was a vertical asymptote. Because that function did factor x plus 3 over x plus 3 times x minus 3. So the x plus 3's canceled, giving us that removable. Okay. Any questions up to this point? So far, so good? Excellent. Yes, Lauren?
On the f of x on the first one on the screen,
Uh-huh.
why was it a positive 6 even though the function came out to be x minus 6?
Okay, x minus 6. I'm looking for the value of x that's going to make that equal 0. So if I plug a positive 6 in, 6 minus 6 is 0. That gives me 0 in the denominator, and we know we can't divide by that. You're welcome. Other questions? Example 2. Use the graph of each function and limit notation to describe its end behavior. End behavior. So I need limit notation. So I will have a limit as x approaches negative infinity of f of x And then I'll have a limit as x approaches positive infinity of f of x. So the first one, the limit as x approaches negative infinity of this function. The function is negative x to the fourth plus 8x cubed plus 3x squared plus 6x minus 80. X is going as far to the left as possible. So as it's going further to the left, where's the function going? Negative infinity. Now we're going to move as x goes to positive infinity. X is getting larger and larger and larger. And as x gets larger and larger and larger, where's the function going? Negative infinity. Okay. Any questions on that? On part B, the equation or the function f of x equals negative x cubed divided by 4 plus 3x squared divided by 4 minus x over 2. Again, I'm going to do the limit as x approaches negative infinity of f of x and the limit as x approaches positive infinity of f of x. This time, let's go with Deja. I want the limit as x approaches negative infinity. So x is going further and further to the left. Where's the function going? Good, positive infinity. Okay. And now let's go with Jessica. As x approaches positive infinity, x gets larger and larger. Where's the function going? Negative infinity. So let's make a point of looking at this. Look at the leading term of this first function. It was what? Negative x to the fourth. The fourth power is even. Even. The leading coefficient is negative. What happens overall when in the very front it's negative? Do you remember from Algebra 2 what happens?
Oh,
It flips. Goes upside down. So when that leading coefficient, or when that power, the highest power, is an even, the end behaviors both go the same direction. Either both up or both down when it's negative. Now look at the second one. Negative x cubed over 4. That power, that exponent, is odd. When the leading term has an odd power, the end behaviors are split. One's going to go down, one side's going to go up. Or it may be split the other way. It's going up, and then it's going down. But that's the way it's going to work. If it's an even power, they're both going the same direction. But if it's an odd power, odd degree, they're split in behaviors. Okay, so just something to keep in mind. Now in example 3, we are going to use logical reasoning to determine the end behavior or the limit of the function as x approaches the infinities, from negative infinity and positive infinity. So this time we don't get to graph it. We just have to think solely about the function. The first one, f of x equals negative 6 over x. Negative 6 over x. And we are going to logically think this through. Oops. The limit as x approaches negative infinity of f of x, and the limit as x approaches positive infinity of f of x. So let's start with negative infinity. Negative infinity. Let's think about some values for x. Let's say x is negative 1. If x is negative 1, what value do we have for y? Positive 6. So at negative 1, we're up at positive 6. Now let's make x get bigger, -10. So then -6 divided by -10 is 3/5. 3/5 or 0.6, a decimal 0.6. So my first point was at 6, and then it's at 0.6. Now let's think about this some more. Let's say x is -100. If x is -100, now what's the value? Positive 0.06. What if x is -1,000? 0.006. So what's happening to those values? It's getting closer and closer and closer to what? 0. So as x is going to -infinity, the function is going to 0. We can logically think through by taking values of x going in the direction we want and making those x values get bigger and bigger. Plug it in, see what happens. Now let's try this going to the right-hand side. The limit as x approaches positive infinity. As x is getting bigger, if we start at x equals 1, what's the value of the function? -6. So 1, -6, it's way down here. Now, x is now positive 10. What's my value? -0.6. So now we're kind of coming up. And then if x is -100, -0.006. So what's it approaching? 0. So we have a pretty good idea of what this graph looks like. We know x cannot equal what? 0. So we have a vertical asymptote at x equals 0, and we just found the values that's basically telling us the graph looked like that and that. Because we said when x is -1, the function's up here at 6. When x is -10, the function's down here at 0.06. At 100 or -100, it was down there at 0.06, and so on. And when x equals a positive 1, we plug it in, we were down at -6. When x was 10, we're at -0.06, and so on. Okay. Let's try the second one, part B. F of x equals x squared minus 5 divided by 3x. So we're going to find the limit as x approaches -infinity of f of x. And then we're going to look at the limit as x approaches positive infinity of f of x. So let's think -infinity. First, we're going to go negatives on all the x's. Let's start out kind of small. X equals -1. When x equals -1, -1 squared is positive 1 minus 5. It's -4 divided by 3 times -1. So -4 divided by -3 is 4/3. Now let's go x equals -10. -10 squared, 100 minus 5, 95 over 3 times -10 is -30. Okay. So what is that? -15/6. Good. Now let's go x equals -100. -100 squared. What number is that? 10,000. 10,000 minus 5 is then going to be 9,995 divided by 3 times -100. Okay, so let's think about this. What's happening to those fractions? Started out at 1 1/3. Now I'm at -15/6. Now I'm at negative 9,995 divided by 300. Where's it going? Not if it's negative. It started out positive and now it's going negative, so where's it going? Negative infinity. Negative infinity. You know, think about if you plugged in negative 1,000. Now think about negative 1,000 squared. Huge. Divided by a negative number is a really big negative number. Okay? So it's going to negative infinity. Now let's go positives. Now x is getting bigger. So if x equals positive 1, if x is a positive 1, 1 squared minus 5 is negative 4. Divided by 3 times 1 is 3, so that's negative 4/3. Now what happens when x is 10, positive 10? 10 squared is 100 minus 5, 95, divided by 3 times positive 10. So now we're at a positive 95/30. Then if x is a positive 100, now we're at a positive 9,995 divided by 300. Now what's happening to these numbers? Getting bigger and bigger and bigger and bigger, going to positive infinity. Okay, so what we have to be careful of here, if I had just x squared minus 5, that would be true. But I have a rational function. I have x squared minus 5 divided by 3x. So when I divide by that 3x, it changes everything. Okay, you're welcome. Other questions? Okay. Example 4. Use your calculator to graph the function. And then on part A, identify any discontinuities, state the type, removable or non-removable, describe its end behavior, and locate any zeros. All right, so let's look at the graph of this one. Let's go y equals. Let me clear that out. I'm going to do a fraction. X squared minus 9 over x cubed minus 5x squared minus 18x plus 72. Graph. Okay, first of all, we were already in Zoom decimal. So do you notice anything when we're in Zoom decimal? There's a hole at x equals 3. Look at this part of the graph. Is that kind of strange? What do you think is happening here? It is a vertical asymptote. There are times, and this is an excellent example, there are times where the calculator, for some reason, does not extend those lines up or down. But the graph does continue to go up and it does continue to go down. So don't always trust everything that the calculator is showing you. Just like the hole. The hole really is there. But if I do standard window, when I do standard window, can I see the hole? No. Now I can actually see the asymptotes better. It extends those lines in both directions like it's supposed to, but we can't see the hole. So always be careful. Trust your own judgment sometimes over what the calculator is showing us. Okay, so first thing, identify discontinuities. Let's go with Josh. What's one of them? Okay, do you remember where that was? Nope, it was actually 3. Positive 3. Okay, so at x equals 3, we saw a hole. And what kind of discontinuity is that? removable. Removable. Okay, let's go Shanae. Do we have another discontinuity?
Yeah, if there's -4,
Perfect. At x equals -4, we see a vertical asymptote, and you said that is non-removable. Excellent. And let's go with Sophia. Do we have another? We have this vertical asymptote, and we have the whole. So what else? At 6. Good. So at x equals 6, what is it? Vertical asymptote, so it's non-removable. Very good. Now part B, describe end behavior. So limit as x approaches negative infinity of the function, and the limit as x approaches positive infinity of the function. Let's go with Emily. Emily, help us out with the end behavior as x approaches negative infinity. Good. As x is getting smaller and smaller right in there, it's going to 0. And then let's go with Maria. What's the end behavior as x is approaching positive infinity? Right here, as x approaches positive infinity, let's look at that. Where's it going? It's going to 0. Good. And then part C, I need zeros. I need zeros. Where is this function crossing the x-axis? Is it crossing at 0, 0? What's one way we could find it? Okay, so if you plugged 0 in for x, what is that going to give us? It's going to give us the y-intercept. Do we need the y-intercept here? Nope. So let's think. If I want the 0, I want the x-intercept. If I just have the function, since I can't really tell on the graph, what do I do to find the 0 or the x-intercept? I'm going to factor. Okay, that denominator is going to be tough to factor, but we always let y equal what? 0. So if y equals 0, 0 equals x squared minus 9 over that huge long thing, which I'm just kind of going to do that for a minute. I would want to get that denominator out of there. So I multiply both sides by that long denominator, right? What happens when I multiply that denominator times 0 on the other side? We get 0. So now 0 equals x squared minus 9. Can we solve that?
Yes, ma'am.
Yes, we can. I can factor. X squared minus 9 gives us x plus 3, x minus 3. So what are my x values? -3 and +3. But we already know what's happening at x equals 3. At x equals 3, it's a whole. So where's our 0 at? -3. X equals -3. Questions on that? So basically, when you have a rational function and you want to know the zeros, you're basically setting the numerator equal to 0 and solving for x. Those are your zeros. Okay. Last one you're going to do on your own. You're going to get to think here. You are going to draw an example of a function with origin symmetry. Origin symmetry, so the same upside down as it is right side up with respect to the origin. where the limit as x approaches positive infinity of f of x equals negative infinity, and the limit as x approaches negative infinity of f of x equals positive infinity. So think about that one and draw a graph that you think works. Okay, one that would work. Straight line, starting from up top and working down. That fits the end behavior limit. Or another one that works is a negative cubic function. Whereas x goes to negative infinity, the end behavior is going to positive infinity. But as x goes to positive infinity, the end behavior is going down to negative infinity. Any questions? All right, excellent. That is it for our notes today.